In this lesson, you're going to have to remember and recall all the different searches and sorts. You're also going to have to know what hashing is and how a stack works. As a revision, you should start this lesson by dividing an A3 piece of paper into 8 sections. In each section, give a title and describe the search or sort that is included in that section. Make sure you leave some space at the bottom of each section where we're going to add data about big O notation. Pause the video now and complete this section. In today's lesson, we're going to be looking at big O notation. There are a series of different big O notations including constant, linear, polynomial, exponential and logarithmic. Throughout this lesson, we're going to be considering how we can measure the efficiency of the different algorithms you just looked at. To start with, it's worth watching this video. This will give you a brief introduction to the topic we're studying today. Please pause the video and complete this section. So here we have two programs. Each program does the same, the program at the top of the page and the program at the bottom of the page. Each program asks for 3 names, appends it to a list and then prints the list. Now when we think of the efficiency of each of them, we'd probably think that the efficiency initially of the bottom program would be the best. This is because it has less lines of code. Well, actually that's probably not the case. When we look at the top program, it's got 9 lines of code. We could say the complexity of this program is 9. When we look at the efficiency of the bottom program, it's a little bit more complicated. We have 2 lines of code which will be printed whatever happens when the programs run, and then we've got 3 lines of code which are repeated in a loop. We could represent this by 3n, and then 1 line of code that will always be printed at the end. Now this is fine when we've only got 3 inputs, but if we were to scale this program up to have 15 inputs, then we're going to significantly increase the amount of processing in both programs. But you'd imagine the complexity of the top program wouldn't change that much. We're only going to be adding an extra 30 lines of code. So in this case, you'd be looking at a complexity of 33. In this second program, it's going to actually be pretty similar, but we can represent it by saying 2 plus 3n plus 1, where 3n is the number of times that for loop is going to be run. So actually the top piece of program is more efficient in this case, but it's very, very marginal. As we said, if there were 30 students, we get a complexity of 63. Whereas we're actually not really bothered about single lines of code. They're actually fairly insignificant when we're running a large program. But when we are writing an algorithm, we need to think about the scale of it, as we've already said. If the data increases dramatically, how will this actually affect the algorithm? So you can see here, if we were to have 30 pieces of code, the complexity would be much larger. There's a common misconception here that the complexity is about how difficult it is for us to write and code an algorithm. That's not the case. We always want to create an algorithm which is going to be as efficient as possible. That means it's going to run as quickly as possible and take up the least amount of space. And we represent these with time complexity and space complexity. We can assess how good an algorithm is by using these two measures. This is where big O notation comes in. Big O notation basically describes the amount of time taken or the amount of memory used by a program, but as it scales with the amount of data it has to work on. It's basically describing the complexity of a problem. Notice how we talk about how the program scales, because if we only have one piece of data, it's going to be pretty efficient. So we're almost thinking about it in the worst case scenario. We measure time complexity, and this refers to the growth in the number of instructions executed, so the amount of time that it takes to run that algorithm. As the length of an array increases, the number of searches would increase, so the time would increase. And the space complexity, the amount of memory that's required for an algorithm, and how that scales as the amount of data increases. So big O notation is a way of us classifying how quickly your algorithm will run and how much memory it will take. Therefore, we can plan appropriate algorithms. So just remind yourself of how a linear search works. Traditionally, we think a program is going to take longer when there's more data to work on, such as a linear search. Remember, a linear search is where we have an array and we search through the data until we find it. Remember, this is not the case for all algorithms. As a recap, a linear search can sometimes be referred to as a sequential search. We search every item one by one. An unordered list is searched for a particular value, and that's a key thing when we're looking at other types of searches and sorts. This can be an unordered list. Each value is compared to the value that we're looking for, or the target value. And a linear search can be implemented with a very basic simple loop. If you haven't done so far already, add to your linear search notes from the last slide and all the details that you need. Now, in this example, we're searching for the target 63. You can see that it's actually at the end of our list. Now, if we are lucky and the value was at the beginning of our list, then this would be quite an efficient search. But big O notation thinks about the worst case scenario, and this would be when 63 would be at the end of the loop. If we had 5 data items looking at number 1, 63 is at the end, we'd have to go through our linear search 5 times to find our value, and that's 5 iterations. Looking at our pseudocode here, we have a for loop. Our for loop iterates round our array. It iterates from value 0 to n-1. We have 5 items in our array. It will iterate from 0 to 4 because remember, our first item in our array is always 0. So our 5th item would be 4. If we found it, we can set our value to true and we can exit our loop. However, we keep going until we've found that iteration. Now with 5 items, that's not too bad. There's 5 iterations. But if we double the amount of data, we need to double the amount of iterations in the worst case scenario. Remember, big O notation is thinking about the worst case scenario and how the time complexity scales. If we were to double our data again to 20 items of data, then it could take us 20 iterations to find our data. So our time has doubled again. So thinking about our complexity and the worst case scenario, and we've got 6 lines of code, this would give us a complexity of 3n. If we forget the end if and the next I, and the exit 4, we've got 3 lines of code. Each of those are going to be repeated a number of times. We don't know how many number of times that's going to be, so we represent that as 3n. Even if we've got 20 pieces of data, in big O notation we're thinking about the scalability. What would happen if we had 50 items of data or 100 items of data? In our worst case scenario, what would happen? So if we only ever needed 10 items, well, that makes it easy and it's a fairly efficient algorithm. But if we're thinking about the scalability of this, we can represent this as 3n. This actually gives us a nice proportional relationship, as the amount of time is proportional to the amount of data. As the amount of data doubles, the time also doubles. You can see an example of a graph here to show this. You need to be able to recognise algorithms which use this time complexity. And you can remember this by the amount of time doubles as the data doubles. And you can see that in the data on the left-hand side of the screen. Can you remember this program from the start of our lesson? Remember, we're only interested in the for loop because those other 3 lines of code have very little impact on the outcome of our algorithm. So let's imagine if we had 200 iterations, 200 pieces of data. The algorithm would still be 2 plus 3n plus 1. It's still the same algorithm that we're using. We'd have 2 plus 3 times 200, which is 600, plus 1, which is 603. So remember, as we double the amount of data, we double the time. So thinking about a linear search, we can represent it with a big O complexity. A big O complexity always has a large O, and then a value inside the brackets. If it's linear, we just put n. We saw our last formula, which was the number of times the for loop looped in one go. So we just put the n in brackets. The rest was insignificant, remember. So for n data items, the time taken is equal to the constant multiplied by n. So in our last experience, it was 3n, but we can just represent this as on. Can you please add this into your notes about the linear search on your A3 paper? So really, just as a recap, for this algorithm, we'd say the algorithm was on, 3n, remember. That is because we had 3 lines of code which could be repeated if we forget the exit and end and next I. So this is our big O complexity of on, or linear complexity. So you now need to explain in your notes what linear complexity is. Linear complexity, we say an algorithm's execution time is directly proportional to the input size. Remember, it grows in a linear way. Think of that graph we just looked at. When you read a book, the amount of time you spend reading a book depends on the number of pages it's going to have. If a book has 100 pages and you read roughly 50 pages an hour, it would take you 2 hours to read the entire book. If we double the amount of pages, we double the amount of time. So here are our rules for calculating big O notation. Add these to your notes in a different colour or underline them, as these are key. The 2 rules we have to follow is remove all the terms except for the one with the largest factor or exponent. Then remove any constants. There was a notation that computer science used to express the complexity of an algorithm, which is named after this German mathematician Edmund Landau. This is the big O notation, and this is what he described. So here is another keyword that you need to understand, the dominant term. Now we'll have a look at how to calculate these equations from pieces of code shortly, but you might have an idea already. With an n squared you'd have 2 nested loops, and n cubed you'd have 3 nested loops. So remembering our rules, here we have 5n cubed plus n squared plus 4n plus 3. Remember, first of all, we think about the dominant term. In this case, it would be 5n cubed. Then we get rid of any constants. So we can ignore the 5, and this would leave us with the n cubed. And that is our big O time complexity, representing that as O and in brackets n cubed. So looking back at this piece of code, we had our complexity of 2 plus 3n plus 1. We look for the most dominant term, which was the 3n. So the first thing we do is forget the 2 and the 1. They're pretty insignificant. We then remove any constants. So the 3 is a constant, so in that term we had our linear efficiency, and that would be ON. Now we're going to look at a range of different classifications. You only need to know 5 of these, and we're going to look at each one in turn. But we need to appreciate how different algorithms fit into time and space complexity. So with our time complexity here, you can see our linear time complexity, O to the n. It's in yellow, the one we've just looked at. You can see there are algorithms which are better than linear complexity, and there are some algorithms which are not good, terrible algorithms. We're going to look at some of those as well. So just so you're aware, we're going to be looking at the following algorithms. That are extras, but for OCR we don't need these. Please pause the video now and write down the different complexities you need to know with their descriptions. Let's think about the constant complexity. This is O1. Now this doesn't matter the size of the input. The execution will always be the same, and we can express this as O1. Let's think about a stack. Remember, items are pushed and popped onto the top of a stack. We have a series of different methods that we can use, such as peek, to examine the item without removing it. A stack is last in, first out, LIFO. The last item to be put onto the top of the stack is the first item to be removed. And we usually do this with pointers. So a pointer will point at the top item in the stack so we know which one to remove. Now we can have two pieces of code, as you can see in pseudocode just here. We've got our operation push and our procedure pop. Each time we run one of these procedures, it's the same code that is used to push or to pop the item from the stack. Now don't get confused here. Remember, if an item is in memory already, then a stack is basically a series of pointers. So all we're doing is changing the pointer in the stack to the new top value when we push or we pop. So the code for each of these procedures is always going to be the same. We're not actually adding or removing anything from memory. So the efficiency of these two pieces of code is constant. So we can say that it takes the same amount of time every time to push and pop from a stack. So it's always the same complexity. On the bottom right hand corner, you've got an array holding a stack with 5 items compared to 10. And it doesn't matter how often we push and pop these values, the time complexity will always be the same. There's one instance when this won't be the case, and that's if we have a stack overflow. So, the time complexity is constant. Because it's constant, our graph will look a little bit like this. Make sure you add this to your notes. You can see as the data grows, the time complexity remains exactly the same. Our next complexity is a logarithmic complexity. But before we actually look at that, let's have a look at what a logarithm is. Now let's think of an exponential. 2 to the power 3 is 8. Hopefully we should know that. When we think about binary, 2 is the base. There are two options, a 0 and a 1. That means that we have a base of 2. When we say to the power of 3, we have 3 bits. So 2 to the power is 3 is 8. That means there are 8 different options we can make. So think about this, 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. all the way to 1, 1, 1. There are 8 different options there. Now, a logarithm is the opposite. It's the inverse of the exponential. So, if we have log 2, 8, that would give us 3. So finding that exponential. If we have a base of 2, so 2 options, and we know we can make 8 different combinations, well, how many bit characters do we need? And that would be 3 to make 8 different options for us. And that is our logarithm. Here's another example. 10 to the power 4. We can think of the base 10 as in our denary number system. 10 to the power 4 is 10,000. So if we've got 10 digits 0 to 9, and we want to be able to make 10,000 combinations, then how many bits are we going to need? Well, that would be 4 in this example. So generally speaking, we can say x to the power of z equals y, and a logarithm would work with log x of y would be z. Try some of these different logarithms. Look at the left-hand column, write them down, and see if you can figure out the logarithmic answer of these. Once you've done, mark your work and check. Now it's worth noting here that as our logarithm increases, we have 1, 2, 4, 8, as that doubles, the outcome actually only goes up by 1. So what is a logarithmic complexity? You need to add this to your notes. With logarithmic complexity, the impact of an algorithm is directly proportional to the logarithmic result of the input size. We can think of a binary search as an example of a logarithmic complexity. With each pass, it actually halves the data. And you can see the time complexity in our table doesn't increase significantly as the data doubles. As the data doubles, our time complexity only goes up by 1. Please look back at your notes on your A3 paper looking at the binary search section. Make sure you've included these details. They're used to search an unordered list for a certain value. They use divide and conquer. So that's halving the data each time and discarding that data. That means that each time the target is compared with the middle value. Half the list is discarded and it's repeated until the target is found. This is highly efficient for large sorted lists. Here is a pseudocode algorithm for this. Now look at the code. This is the only example here where we seem to have a loop, but it's actually an efficient loop because it's halving the code. In the exam, if you have to recognize a binary search, remember you're looking for something that recognizes the middle of the data set. So you're going to have some 2 pointers, a high and a low. It's then going to divide that in the center and then do some form of comparison to find out if a data value is higher or lower than that value. We could even actually implement this as a recursive solution, so that's why it calls itself. But even if we were to do that, the time complexity is actually going to halve, and that's because we're halving the data set. The one issue with a binary search is that it must be a sorted array. If it's not sorted, you cannot do a binary search. So if we don't have an assorted array, it is going to add more complexity to it. Let's have a look at an example. Our target here is 63. We've got 10 data items. We split it down the middle, and the middle item is 58. We know that it's larger than 58, so we can discard the lower values. We're left with 62 to 95. We run the algorithm again and we repeat it until we find our value. So this time we find the middle value of 85 and we realise it's less than 85 and discard the top values. We're left with 62 and 63. So actually it would only take 3 iterations to find this value when we've got 10 data items. If we double the amount of data, then it's actually only going to take us 4 iterations. If you look at the diagram on the right hand side, you can see we found it in 4 searches. This is much more efficient than a linear search, because remember, in a linear search, if we doubled the amount of data, we'd double the amount of time. In this instance, we've doubled the amount of data and we've only added 1 iteration. If you do maths, then you'll recognise this graph. This is a logarithmic graph. You can see the data on the left hand side doubling, but the time is only increasing by 1 value. That means the graph will slowly almost level out but go up very, very slightly. Because it's only increasing by 1, this means that as the data increases, the performance degradation is not significant. Now sometimes a binary search can be called a binary chop. So we can think of a binary search complexity that as we double the data, it only requires 1 extra chop. This makes it very efficient for large data sets in particular, but remember, this is only if the data is already sorted. This gives us a time complexity of logarithmic, and we represent that by O log n. Please make sure you add this to your notes, add it to your binary search, and then explain what O log n is. We're next going to be looking at polynomial complexity. An example of polynomial complexity is a bubble sort, and you can see some pseudocode for this on the left hand side of the screen. Remember, with a bubble sort it compares every item to every other item. So for this to work we need 2 for loops, each of them nested inside the other loop. So with polynomial complexity, the impact of the algorithm is directly proportional to the square of the input size. You need to make sure you make notes on this complexity. If we have an array that contains 4 coloured dots, we want to compare each one to each other spot to check if there's any repeated colours. We'd need to do 16 comparisons. An example of polynomial complexity would be a bubble sort or an insertion sort. Sometimes this can be called quadratic complexity. We can tell it's quadratic because there are two loops, a loop within a loop, or nested loops. However, if there were three loops, this would then be cubic complexity and not quadratic complexity. Find your page about bubble sorts and then add to your notes and make sure you've got this data. A bubble sort sorts a list of items into numeric or alphabetical order. It scans the list and the pairs of values, swapping their positions if necessary. For n data items, the list is scanned n-1 times. And there are actually various enhancements possible. Here's a bit of pseudocode for our bubble sort. You can see the inner loop, our second for loop, is comparing the items. As we move through our bubble sort, it compares each item. Our outer loop is ensuring that the loop runs n-1 times until there's no swaps. This is actually an example of an algorithm of how a bubble sort works. Watch how it compares every item, and then it continues to compare until there are no swaps. Once there are no swaps, it knows it's reached the end. Here you can see we have doubled the amount of data, and this actually takes more than double the amount of time. In this visualization, you can see that it actually speeds up a little bit, and you can see how long it takes. Can you imagine doubling this again? Here's the graph of our polynomial complexity, an example of the bubble sort. As the amount of data increases or doubles, the time more than doubles. This is not an efficient algorithm. Make sure you add this into your notes. We can think of our bubble sort complexity in the following way. We have n-1 times n-1 operations. Mathematically, this can be written as n squared minus 2n plus 1. Remember our two rules. The first thing is we look for our dominant term, which is n squared. Then we ignore any constants. So the big O complexity is quadratic. So our polynomial complexity is O with n squared in brackets. So for those of you who are aware of an enhanced bubble sort, you'll know that the largest item is in the correct position after the first pass. So you can see in this instance 10 is always going to be in the last position after the first pass. After the second pass, the second largest item will be the second to last item in the array, and so on. So that means the inner loop can run one less time with each pass of the outer loop. we can actually make a simple change to our algorithm to reflect this. So when we said in the loop, and it's highlighted in red, O to n minus 1 minus I pass. This means for an enhanced bubble sort complexity would end up with the following: n minus 1 plus n minus 2 plus n minus 3 all the way to the end until we have 3, 2 and 1 operations left to go. Now this can be represented as n squared minus n divided by 2. Even in this case, we don't need to check the last time. Remember, we in our usual bubble sort would have to check that every data item was in the correct position before finishing. We don't need to do this in this complexity because we know that they're all in the right position once there's no swaps to do and our value gets to 1. This is actually good in practice. There's a 50% reduction in the time taken. But this is big O notation. It might be slightly enhanced, but the dominant term is still n squared. It's still quadratic. And all the time, even though the time is reduced by 50%, we think of the worst case scenario and scaling. So when we think of the bubble sorts, the best case scenario is actually linear, that all the data items are already in the correct order. But we're only interested in the worst case scenario. Let's say data is in the reverse order and every item has to be moved. That gives us quadratic still, O n squared. So even when we are removing data items each time and reducing the amount of searches we have to do, as we increase and scale the data, it's still a quadratic efficiency. And that's the key thing here. An algorithm can be written as quadratic and still be more efficient than some other algorithms, but as you scale that data, it's going to be inefficient. The final one we're going to look at is exponential search complexity. This is represented as O 2 to the power of n. It takes a significant amount of time as we increase the data. The time it takes to execute will double with each additional item. So where we've seen the items before double and the time doubles in a linear complexity, exponential, it grows more than double when the data doubles. Well, this one, for every input item, it doubles. So, for example, 10 items will take 1 minute to execute, 11 items will take 2 minutes, and 15 items would take 32 minutes. So you can see, only by adding 5 extra items, we have added a significant amount of processing time onto our complexity. This has massively poor scalability and should be avoided at all costs. We've seen this complexity graph before. Remember, you're going to have to be able to recognize the different graphs. But this is a quick comparison, and we can see each of the different types of complexity and operations side by side here. An algorithm with exponential time complexity might actually, though, be okay on a small data set, but it would very quickly become unusable. This is a quick reminder about what happens if we have multiple functions in code. You can see 4 sections of our code here. I put the time complexity by the side of each one. When we add them up and create a formula, remember we look for the most dominant term, the term with the largest factor, which is O n squared. We remove any constants, so actually the time complexity for this whole program is now O n squared, just because of the code in section 3. Here's a quick cheat to help you to kind of figure out when looking at code what the complexity might be. If there's no loop, it's likely to be constant, O1. Anything that's halving the dataset is logarithmic, and this is the one to be careful with, because this might have loops, a for loop and a while loop. So make sure when you're looking at a loop, you check first of all to make sure if the dataset is being halved. Remember, you're looking for pointers, the start and the end of an array, the data halving each time, and the pointers moving. A cheat for looking for linear is a for or while loop, but again, in the exam, make sure it's not halving the dataset. Polynomial will have a nested loop, and if something is recursive or calling itself, it's likely to be exponential. You'll find with this lesson a big O notation cheat sheet. This will give you a little bit more information and examples of all the different types of efficiencies that you need to know. It's a really good tool to help you to prepare to revise. Have a look at it, make sure that you've added everything into your notes, and just check that you're okay with it. So far we've considered time complexity, but we also need to think about space complexity. This is the amount of storage that an algorithm actually takes on a computer. It is often represented in the following way. OON. Think about recursion. When the computer is calling itself, it's making an extra copy of the code and the data. This would increase the space complexity. So to reduce our space complexity, the key is to perform all the changes on the original piece of data. Here is a space complexity table. The space complexity is shown in the last column. Notice how we're still using the same form of big O notation this time. Bubble sorts and insertion sorts are O to the 1. The data is not actually changing. We keep the same array. With a merge sort, it's O to the n, linear. And a quick sort, it's O log n. With a quick sort, remember, we can get rid of data that we don't need, almost halving the amount of data. With a merge sort, though, we're merging values. Remember, we split these into different lists every time until we compare them and merge them back together. Here are two ways to think about developing an algorithm for large data in a database. If you have a lot of data, but the data needs to be processed quickly for a future update, then you need to pay more attention to time complexity rather than space. If you have a lot of processing power, then your time complexity isn't as important as you might think. Therefore, you might want to focus on space complexity to make sure you aren't wasting a lot of data. Your homework is to watch the Craig and Dave video looking at the complexity of a game. This will give you some examples and put it into practice some of this theory. Make sure you make notes to explain what is happening. You now have a series of tasks to complete in your workbook. Have a look for these different tasks, try and complete them, and then mark them. Now, there are lots of exam questions in this topic. That's because it's one of the easiest topics for the examiner to assess. You often have to show knowledge of the different searches and sorts, as well as the efficiencies of the algorithm. So it shows a really deep understanding of computer science. So we're going to take extra time practicing these. Look at the exam questions, please. Then mark your work and make improvements. Extended exam questions are common with this topic. So try an extended answer and then use the mark my work task to see how well you've done. Try another extended question and try improving your answer again.